Hello everyone, today we're going to be working on example 5-4 and this example is asking us to calculate the reactions for the beam loaded as shown. So the first thing that we're going to do is we're going to see how many reactions we're going to have. As you guys could see, we have a fixed end, meaning that we are going to have a X reaction. We're going to call this A of X. Then we're going to have a Y reaction. I'm going to assume upwards. We're going to call this A sub Y. And we're going to have a moment. And I'm going to assume counterclockwise. We're going to call this M of A. So now that we know that we have a moment, a X reaction, and a Y reaction, the next thing that I'm going to do is now I'm going to determine the concentrated forces on this loading that we have on the beam. What I'm going to do is I'm going to be splitting this loading into two shapes. So that way we're going to have a loading of like a rectangle and then a loading of a right triangle. So I'm going to start or cut off right here at the 50 pound-feet mark. So that way we know the height of this triangle, which is going to be 50 pound-feet. And now for the right triangle, instead of it being 100 pound-feet right here at this point, what we're going to do is we're going to subtract the 50 pound-feet that is now only in this rectangle. So that means that this part right here is also going to be only 50 pound-feet. So now that we know that, we're going to determine the two forces. To start off for our rectangle, we know that that location of that concentrated force is going to be right at the midspan of that beam. So we know that it's going to be about here. We're going to call this force R1. And then from there, we have this right triangle. As for the location, we know that it's always 1/3 away from the highest point of the right triangle or 2/3 in. So we know that our R2 is going to be somewhere around here. So now we're going to determine that the magnitude of each of those concentrated forces. So for R1, to determine the concentrated force, we're going to do, since the beam is 9 feet long, we're going to do 9 feet times the 50 pound-feet. That ends up giving us that our first force is equal to 450 pounds acting downwards, obviously. And then for our second force, R2, we do 1/2 of, once again, the span of 9 feet times, we said that the highest point now is 50 pound-feet, so times 50 pound-feet. That ends up giving us that our second force, R2, is equal to 225 pounds, also acting downwards. Now for the location, I'm going to be determining their locations from point A, since we're trying to calculate the reactions on the fixed end, and our fixed end is point A. So like we said, R2 is from point A, 1/3 of the span. So the location for that's going to be for the second one, is equal to 9 feet times 1/3. So we end up getting that location is at 3 feet from point A. And for our first force, like we said, it's going to be found midspan of that rectangle. So we have 9 feet times 1/2. So we know that that's going to be 4.5 feet from point A. So now that we have our two concentrated forces and their locations. Now we're going to proceed to calculating the reactions. So I'm going to start off with our forces in the x direction. So sign convention, anything to the right is positive. And we know that the sum of our forces in the x direction have to equal 0. From there, we know that the only force in the x direction is our A of x. We don't have any more horizontal forces, so we end up getting that our A of x is equal to 0. That's our first force, our first reaction. Now from there, I'm going to be determining our A sub y. So sign convention, anything going upwards is positive. We know that the sum of our forces in our y direction also have to be equal to 0. So we assume that A sub y is going upwards, so that's positive, A sub y. From there, we have the two concentrated forces that we found, which they're both acting downwards, so they're going to be negative forces. So a negative 450 pounds and a negative 225 pounds. And we know that that has to equal 0. We end up getting that A sub y is equal to 675 pounds. We ended up getting a positive number, meaning that we assumed correctly. So we do know that A sub y is going to be acting upwards with a force or magnitude of 675 pounds. Now to determine the moment at A, we're going to be taking the sum of the moments about point A. So sign convention, counterclockwise is positive. We know that the sum of our moments about point A also have to equal 0. So we assume that the moment at A is counterclockwise, so that one's positive. From there, we know that A sub x is equal to 0, but either way, it's not going to be creating a moment. A of y, once again, not going to be creating a moment. The only two forces that are going to be creating our moments are our two concentrated forces that we found. They're both on the right side of point A, meaning that they're both going to be creating a clockwise moment. So that means that they're both going to be negative moments. Remember, moment is equal to force times distance. So our forces are right here. And like I mentioned earlier, I wanted to find the locations from point A. So our distance are exactly our locations. So we have our first force, which is force 2. We know that it's going to be negative since it's going to be creating that clockwise moment. So our moment is equal to the force, 225 pounds, times the distance, 3 feet. Another negative moment, our force of 450 pounds, times our distance, 4.5 feet. We know that that has to equal 0. So if we solve this for the moment at A, we end up getting that our moment at A is equal to 2,700 pound-feet. This number came out positive, meaning we assumed correctly. So we do know that the moment at A is going to be going counterclockwise. And with that, we are done calculating the reactions for the beam. So once again, the first thing that we did is we determined how many reactions there were going to be. Since it's a fixed end, we knew that there was going to be the 3 reactions, the moment, the force, our x force, and our y force. From there, we had a loading going on this beam. So from there, we took this loading, split it into 2 different loadings to be able to determine the concentrated forces for this rectangle and then this right triangle, since we know how to find those concentrated forces for both of those shapes. From there, we determined their locations also of those 2 forces from point A, because we were going to use that later on. From there, we just determined the sum of our forces in our x direction, giving us our magnitude of our reaction AX, which we found out to be 0. From there, we did that for our forces in the y direction, giving us the value of A sub y is equaling 675 pounds. And then from there, we took the moment about point A to determine the value of the moment at A, giving us 2,700 pounds going counterclockwise. Thank you guys so much for watching this video. Please feel free to hit that thumbs up. And also feel free to subscribe to our channel if you guys would like to see more videos like this.